how we perform chemical changes. So today, I want to make sure we understand what exactly is a chemical reaction, what is a chemical equation, what is the anatomy? If given a chemical equation, what is all the information about the chemical reaction that's revealed? And then how do we balance a chemical reaction? Okay, so first, in the student packet, so no need to write any of this down, but you have it in your packet on the very first page. These are all of the things that we will be able to do by the end of the chapter. So if you want to check back and just make sure that you can answer these yourselves, these are the goal. The overall reaching skill that you will have by the end of this unit is if just given the name or names of your reactant, you will be able to create a balanced chemical equation from it. I know it may seem like, well, that doesn't seem very hard, but that will incorporate so many skills that we've accumulated and we'll learn this unit. So our unit exam will be exactly like this, but probably 40 of these. And you'll start by getting the formula of your reactants, and then knowing what the reactants are, you'll know what type of reaction it is. So be it a single replacement, combustion, double replacement, composition or decomposition, you'll be able to get the products, get the right formula, and balance the equation that results. You will be just wowed at yourself and what you'll be able to do by the end of our unit. So that is where we are ultimately going. So first, chemistry is a study of matter and the changes it undergoes. Chemistry is a study of matter and the changes it undergoes. Remember in chapter 1, we learned that there are 2 kinds of changes. All right, so I'm just going to ask you to try to remember what is the difference between a chemical and a physical change. So of all the ways we can change matter, these are the 2 categories. Do we remember what sets them apart?
Like a physical change, just like a change in like size or shape, or a chemical one, you're actually changing the substance, like maybe the chemical formula of it.
That is excellent. So if you could add to that, you said a chemical change is when you're changing the chemical substance. Okay.
Like the makeup of the substance.
I love what you said. Okay, let me change up my camera if you don't mind. Okay, so a physical change is you've altered your substance in some way, shape, or form. And I love that you said, what shape? Here, let me just make sure that I'm getting. Okay, so So in a physical change, we are altering the substance in some way. Okay, so it wouldn't be a change unless something was altered. And so maybe the shape. So if I cut this piece of paper or crumbled it up or tore it, maybe the state, maybe I am melting a solid into a liquid. Maybe dissolving. But the chemical nature is not altered. So, for example, if we take sucrose, table sugar, and place it into water and just dissolve, and so make sugar water or a solution, the sugar has not been chemically changed. We can, with very gentle heat, drive away the water and retain the sugar back. The sugar is still sugar. Sucrose is C12H22O11 in formula. You'd never be expected to know that. Well, all that you're doing is just surrounding every sugar molecule with water molecules. You are not changing the formula. But in a chemical change, for example, when you roast a marshmallow, when you roast a marshmallow, which is mainly sugar, and if you're like my daughter who just doesn't waste any time, she just puts that marshmallow right in the flame, well, then you're causing a combustion reaction, not just a Maillard reaction, but a combustion reaction, and you're burning it. And then some other byproducts. But you are forming new substances. And I think, Jack, did you say, shucks, didn't you say something about new chemical formulas?
Yeah, like the chemical makeup has changed.
Yeah. So do you see here, carbon is bonded to hydrogen and oxygen, and it's in a much different ratio. Here, it's only bound to oxygen, and it's in a different ratio than in sucrose. So a chemical change is a brand new substance with a new chemical identity. Is created. And it's not a simple physical change that you can undo the chemical change. You know, think about making scrambled eggs, cooking, baking, that's a chemical change. It would be very difficult to unscramble your scrambled eggs once the heat has been applied, and so on. Okay, so chemical reactions are chemical changes. They are just another way. So also known as chemical changes are also known as chemical reactions. Chemical reactions. And we represent chemical reactions with chemical equations. Okay, chemical equation. So we'll often use these synonymous. Like I may say balance the chemical reaction, but I'm talking about the chemical equation. So these are often used synonymous because this is how you symbolically represent a chemical reaction. All right, I have something neat to show you guys. So, and I want to preface this with, this is showing us just, don't you know, like the stereotypical chemists. When we imagine chemists, I think this is what we think of. But they are going to perform for us the reaction that's also often nicknamed the thermite reaction. So it's just about a minute or two, but it's definitely worth watching. And it just beautifully represents what we just kind of wrote on paper. All right, so let me bring this up. And the thermite reaction involves rust. You don't have to, but the easiest kind of ingredients for the thermite reaction is rust. I'm so sorry, bringing it up, and aluminum. Oh, shucks. I have to make sure that I'm so sorry. I have to make sure that I shared the sound. I love Zoom, but all the things sometimes that you have to make sure you've clicked, a little annoying. All right.
Hey, welcome to the Rochester Museum and Science Center. Thanks for joining us. Today, it's thermite. And thermite's been around since the 1800s. It's a single exchange reaction. You take two different things and you put them together and it makes a new thing. The two things we're going to take today, one of them is aluminum powder or aluminium if you're from the other side of the pond, and the other is just iron rust. So what we're going to do is we've got a little bit of a igniter on the top, and I'm going to take some sulfuric acid and drip it on top of it. When it does, it's going to cause a chemical reaction that's going to superheat this from whatever it is outside right now, somewhere in the 50s, to about 2,300 degrees Fahrenheit in about 2 or 3 seconds. So you'll be able to see a cascade of iron, and then afterwards we'll take a look at it. Here we go. Ready? That's all inside there. Once it cools down, we can turn around, crack it open, and you'll have usually little BBs of metal, really bright, shiny metal. This one came out pretty well. Thanks for joining us, and we'll see you next time here at the Rochester Museum and Science Center.
All right. So how did that, Chris, represent what we said chemical changes are? Oh, I'm sorry. Okay, take it away, Chris.
It both generated heat and formed into a different substance.
Ah, so I think that we're all familiar with aluminum foil. And what they did, now they started the reaction by doing a little reaction. So you talked about sulfuric acid, we can totally ignore that. So they took powdered aluminum and just heated it in the presence of rust. And rust, Fe2O3, and I think in some way, shape, or form, we've encountered that in our life. And what was formed were these products. Okay, so what I'm showing you, you know what, I should write it this way. That's very silly of me. Let me just jot it down real quick again. So solid is iron 3 oxide reacting with aluminum powder, and they made these products. Okay. So Jack, you said in a chemical change, a chemical reaction, new things are formed with new chemical identity. Prove it. How is this showing that?
So in your reactants, you had rust, and after it reacted, you just have iron in the solid state and not rust. Your oxygens came over to your aluminums.
Wonderful. Absolutely fantastic. So we can just examine what's going on here. This is elemental neutral aluminum. I don't have elemental neutral aluminum on this side. Aluminum became a positive 3 cation, and it is bound to oxygen, metal, non-metal, we would know through ionic bonding. This is an ionic solid. Well, here, iron is a positive 3 cation. Here, it's a neutral compound, or neutral compound, neutral in its elemental form. But here, and metal, non-metal, it also is ionically bound, but it is a different ionic solid than this. We know metals on their own and the characteristics that they have, they are malleable, they are silver, lustrous. Iron is magnetic, more magnetic actually than aluminum is. So if we can just even think, you know, in these this compound and this, okay, they have their own identity. Well, then we're going to produce a product and products that have different properties, characteristics. We're making something that's more metallic than we started with, more magnetic rather, more metallic. What am I saying? So we are forming new substances. Let's see what we think about this kind of definition. A chemical reaction, yes, is a chemical change. But I think it's better to say a chemical reaction is a process in which chemical bonds are broken, atoms rearranged, new chemical bonds formed, which results in the creation which results in the creation of new substances with new chemical and physical properties. And I hope that we can see the breakdown of this definition with this chemical equation. Chemical bonds are broken. So the attraction, the ionic bond between the iron and the oxygen was broken. The atoms got rearranged. The aluminum is now paired with the oxygen and the iron is not. Well, that happened because a new ionic bond was formed, and then we create new substances with a different set of chemical and physical properties. I think that example, we're going to come back to this because there's something that's missing here. Something that's missing. Okay. I really, really like that example of reaction because I think it was so, let's say it was a spectacle to see. Sometimes there's a clue during the chemical reaction that lets you know a chemical change is occurring. Chemical reactions, yes, involve the breaking and forming of bonds, but they involve changes of energy, and often that can be observed. So do you remember also in chapter 1, we talked about evidences of chemical changes. And commonly, there's 4. Now, if we don't see these 4, that does not mean we are not getting a chemical change. And a reaction can possibly involve more than one of the evidences. Okay, so I betcha, Christina, you remember one of them, or what did you observe during the reaction that we just watched that really stood out?
Is it, I don't think I remember any actually.
That is okay. That is okay. Can you phone a friend? Who should we ask?
Lexi.
I don't really remember any of them either.
Who should we ask?
Peyton.
Peyton, do you remember?
Isn't releasing gas one of them?
Oh, it is! Yes! Now, if our reaction, Tyler, releases a gas, how can we see that?
Like an explosion or?
Sure, and I think that's like the scale we'd like, is that it's an explosion. And usually that's what causes an explosion. It's a release of gas, and that buildup of force explodes the container. And that gas has to expand somewhere. So usually when there's an explosion, yeah. Okay, but you know me, and my job is to keep us safe primarily and to teach us some chemistry. So it would be irresponsible if we did a lot of explosions. We'll do some if we did a lot. But we're gonna do a heck of a lot of reactions where we produce gas. How can we tell?
Is it that it bubbles?
Yeah. So we usually see bubbling. Yeah. So bubbling is the observation and then producing a gas. Yeah, very good. When we just watched that thermite reaction, why did they do it outside?
Is it like a change in temperature?
Oh man. In fact, there was such a change of temperature. How did you know there was a change of temperature?
There's like that molten liquid.
Yeah. So we can release heat. In fact, I mean, that reaction was so, and Zenek, I know you know, reactions that release heat. We usually use a certain term. It starts with an E and then an X. Yeah, exothermic. It was so exothermic that it actually energized the electrons of your iron, releasing light. Yeah, releasing light. So if it releases heat, but we know there's a lot of reactions that can absorb heat. And if it's absorbing, we know we would use endothermic. Okay. So that's kind of the change of temperature. But there were also sparks that were seen. And so not only did the metal get its electrons energized enough to release heat, but there were also other things that were doing that. So the other is if it releases light, which that's not as common, of course, as the change of heat or change of temperature and releasing light. And the fourth, now there can be other things, but like there's no denying that you are definitely performing a chemical reaction if you produce a precipitate. Okay, if you produce a precipitate, and a precipitate has a special definition. A precipitate is a solid produced from the mixture of two or more solutions. Okay, solid produced from the mixture of two or more solutions. And we will see plenty of examples of these. Plenty. Okay, so this chapter is all about chemical reactions. In a chemical reaction, we are forming one or more things that have totally new chemical and physical properties than what we started with. We're familiar with rust. It is very brittle. We understand the color of it. Aluminum, understand that. And then what was produced, now what they pulled out of the sand was, of course, that molten iron, but the other product was kind of like a white powdery. Aluminum oxide is white and powdery. So we're producing things of totally different observable properties, just in color, but also in chemistry. Okay, and we're lucky we can get evidence during the chemical reaction that is definitely telling us we are forming new substances because these involve a change in energy. Remember, delta means change in energy, which accompanies chemical changes, chemical reactions. So these can be representations of that. Okay, any questions before continuing? All right, can we talk about the anatomy of a chemical reaction? The anatomy. And I believe, Jack, if I'm not mistaken, you used beautiful terms when you were telling me about a chemical change. All right, so this is an example of a chemical reaction that we saw. Okay, I hope we're okay that I'm just leaving those there. All right, Jack, can you remind us again, sir, what do we call the things on the left side of the reaction arrow?
Reactants.
You got it. Reactants. And what about the things on the right side of the arrow, sir?
Product.
You
Product.
got it. So reactants are the beginning ingredients, and then product or products are on the right side of the arrow, always. So this is what we're starting with, and this is what we hope to be ending up with. Okay. These little letters in parentheses. Okay, these are called phase symbols. Phase, P-H, oh, that did not come through well, so sorry. P-H-A-S-E, P-H-A-S-E symbols, phase symbols. All right. So Olivia, I am sure once I list the different phase symbols that you'll be able to tell me what they represent. So we could have a lowercase s, we could have an L, but usually it's a cursive L. We can have a G, and we can also have an AQ. So Olivia, what do you think the S stands for?
Solid.
You got it. The L?
Liquid.
Yeah. G?
Gas.
All right. These are the states. So the reaction that we observed, they reacted two solids and they made two different solids. A very common phase that we will see a lot in chemistry is AQ. Dylan, do you have a prediction as to what AQ can represent?
I do not.
Who do you think might?
Maybe Matt.
Aqueous.
What does that mean, sir?
It's like the reaction occurred in water.
Ah, okay, well, if I can just perfect what you said a little bit. Aqueous, A-Q-U-E-O-U-S. We know aqua relates to water in some way, shape, or form. Aqueous means that substance is dissolved in water. And so you're right, water's going to be there in the background where the reaction is happening. So for example, if we would have NaCl, AQ, that just means the sodium chloride is dissolved in water. Okay, so it's telling us the form of our substance. These are the main ones that we will see. Okay, in a moment, we are going to be introduced to coefficients. So in this reaction, what I was missing were numbers written in front of the chemical formulas. If a number is not written there, it's understood to be 1. And usually we just don't write the 1. And so subscripts, if they're in parentheses with a letter, they're phase symbols. Subscripts, though, are usually meant to, of course, identify how many atoms of each element we have. These are coefficients, and we're going to talk about in a little bit what they are meant to do. Okay, but that's the proper name, coefficients. So coefficients are written in front of chemical formulas, and they're as large as the chemical formula. You would only ever add a coefficient in front of an entire chemical formula. Coefficients are never added within a chemical formula.
Would you always write 1, or is that just assumed due to the fact that you write it?
It is assumed to be there. I would never mark it wrong if you wrote it.
All right, thank you.
Okay, yeah. All right, there can be some other things that are conveyed to us within the chemical reaction. Now, before I forget to say this though, it doesn't matter the order that reactants come or products come. So it would be the same thing if I wrote Al2O3 plus 2Fe. Okay, the order of the products doesn't matter. The side of the arrow they're on matters. So as long as a product is to the right of the arrow, it doesn't matter the order. Just like 2 plus 3 and 3 plus 2 are the same. It doesn't matter. Okay, so the order, but the side of the arrow matters. All right. Experimental conditions can be conveyed to us within a chemical equation as well. So, for example, the reaction that the chemist did for us needed an input of heat, and that was given through performing another chemical reaction. Usually we represent that with an open triangle. An open triangle above the reaction arrow means heat was added. But you may need to run your reaction at a specific temperature. And so you could also indicate that above the arrow, especially if we need a low temperature, let's say -10. And so that would be, the temperature reaction started at. Sometimes a reaction needs increased gas pressure. And we will get near and dear with gas pressure when we study gases more deeply. And so if we needed to add pressure, the most common pressure unit is in atmospheres. And at sea level, which we're pretty much there with average weather, we experience about 1 atmosphere of pressure. So if you needed something like 2.5 atmospheres, you would indicate that over the arrow. Okay, sometimes we can use a catalyst. For example, we have some idea, but not exactly why, but a fantastic go-to catalyst is MnO2. We'll use MnO2 as a catalyst a lot. If we use a catalyst, we write it over the reaction arrow. Anthony, what do you know about a catalyst, sir?
I don't really know. Like
Anything. What do you know from biology? What did you learn a catalyst is all about?
isn't it like a cap or something like? I forget what it is.
That's okay.
Yeah, sorry.
That's all right. That is all right. Who do you think can aid us?
Mason.
Catalyst, sir. Do you remember anything?
Not really.
So who should answer that for us?
Probably Matt. It like speeds up a reaction.
Do you know how?
Well, like if you would like add heat to something, like the particles, I guess it is not very scientific, but they like move faster.
Okay, but then that's heat.
Oh.
A catalyst in and of itself is a
lowers the
chemical
activation energy.
Oh my gosh. Yeah. By lowering activation energy. That's how it speeds it up. Every reaction requires some initial input of energy, some initial input, and that's called activation energy. So for example, when we strike and add a spark to our natural gas to get it to combust, we are adding the activation energy. Well, the catalyst lowers that. So it's just easier to produce product, and so it'll go faster. But there's something else about a catalyst. A catalyst is unchanged chemically by the reaction. It is unchanged. In a chemical reaction, we are writing what does get chemically transformed. Okay, that's what shows up. How are these appearing after or because of the chemical reaction? Well, a catalyst doesn't get chemically changed. So that is why it is written above the reaction arrow, because otherwise it doesn't have a place because it doesn't get chemically altered. Okay, that's why it's written above. The other thing, if you are producing a precipitate, so let's just say reactant A and B produces C plus D, and we are reacting something dissolved in water with something dissolved in water, and we create a solid, no longer dissolved in water, and then another solution. A solid produced from the mixture of two or more solutions is a precipitate. And the way that we can see that is it gets cloudy, but also this is no longer soluble in water, so it will fall to the bottom of your vessel. And so sometimes in a chemical reaction, you'll see a down arrow. And what that means is you're producing a precipitate. We could see the down arrow in addition to the phase symbol, or phase symbols may be absent, and that's letting us know we're forming a precipitate. Now, we could also be, let's just say, reactant Shay produces G plus L for Lexi. Well, what if one of these is a gas? Well, another way to represent that is with an up arrow. And so that can represent a gas. So you can be told a lot just with letters and symbols about the experimental conditions. Okay, any questions? All right, so let's see. Haley, would you like to make water or ammonia? Just choose if you don't mind.
Water.
Okay, let's make water. All right, so water is reacting hydrogen gas with oxygen gas. And we need, oh, this is great because I forgot. Please forgive me. Okay, Hallie, if you haven't kind of picked up, I have no artistic skill. I am so sorry. So please use your imagination. That is supposed to be a lightning bolt. That is so pathetic. A lightning bolt above the reaction arrow means the input of electricity. So we need a big input of energy to get hydrogen gas to react with oxygen gas to actually make water. And Haley, do you want to make it in the liquid or gaseous state? It doesn't matter.
Liquid.
Sure. And it depends on the input of electricity. It might yield in the gaseous, but then would quickly condense and give us liquid water. All right. There is a huge problem with this reaction. A huge problem. Well, let's check chemical formula. We know that hydrogen absolutely always is +1, oxygen -2. So we know plus, of course, that's the most commonly known formula, I'd say. Well, what about these elemental forms? All right, do you remember? I don't expect us to. I hope it's somewhat recognizable that we said there are 7 elements that naturally bond with themselves. We call them the diatomic elements. Diatomic elements. There are 7. Well, hydrogen is one of them. So naturally, we do not find hydrogen as H. It actually bonds with itself to form H2. The next is nitrogen. It's not found as N, it's found as N2. Then oxygen, not found as O, it's found as O2. And then our halogens, fluorine, chlorine, bromine, and iodine. We need to know these are our 7 diatomic elements. And remember I showed us before, hydrogen, all right, but the others, starting with nitrogen, it makes a 7 on the periodic table. And how perfect that there's 7 diatomic elements. Now, of course, sorry for hydrogen, use your imagination, but it kind of makes a 7. Okay, so these formulas are correct. These formulas are correct. Now, if we wanted to make rust, well, we would just expose iron, and iron is not one of the 7. So any element that is not one of these 7, we write it without any subscripts. So iron exposed to oxygen. Oxygen's one of our diatomics, so we would write it as O2. So we call these, even though they're chemically bound, they're covalently bound, they're compounds, but we say they're the element form of these 7. And then we form Fe2O3. Okay. Well, again, back to this reaction. So all of our formulas are fine. And you don't have to come up with these phase symbols yet. So they're fine, I promise. But what isn't fine is this. Okay, Shelby, if you could help me out counting the number of atoms of each element on the reactant and then the product side. So as this is written, how many atoms of hydrogen do we have?
There's 2 hydrogen and 2 oxygen.
Perfect. How about on the product side? How many hydrogen and oxygen?
There's 2 hydrogen and only 1 oxygen.
So we violated one of the foundational guideline rules of chemistry. We destroyed some oxygen. That's what it looks like. Some oxygen disappeared, and that can't be. The number of atoms of each element on the reactant and product side have to be the same to uphold the law of conservation of mass. And that's where coefficients come in. That's where coefficients come in. When you write a coefficient in front of a chemical formula, it multiplies how many subscripts are there per the formula. So this coefficient of 2 in front of aluminum means I have 2 aluminums. If this would be a 4, I would have 4 aluminums. If it's 5, I have 5 aluminums. On the rust, it's Fe2O3. With a coefficient of 1, that means I have 2 irons and 3 oxygen. But if this changes to a 2, then I have 4 irons and 6 oxygen. So the coefficient multiplies the subscripts. And it doesn't just apply to one, it applies to all the elements. The same with, let's say, magnesium nitrate. If I need a coefficient of 3, then I have 3 magnesiums, 6 nitrogen, and then 12 oxygen. Yeah, because if this is a 1, I would have 2 nitrogen, but with the 3, they would multiply to be 6, and then with the 3, they'd multiply to be 12. Okay, I get you for 3 more minutes, but I will just keep you for 1 if you don't mind. Okay, we will leave balancing for tomorrow. We will leave balancing for tomorrow. Okay, Tyler, this chapter is on chemical reactions. Chemical reactions. So, at the dinner table tonight, when you get asked, what did you do in chemistry today? You said, started our new unit on chemical reactions. And then you get asked, well, what's a chemical reaction? What will be your response?
Hey, Mr. Raider.
What we wrote down earlier. So the process in which chemical bonds are broken, atoms are rearranged, new chemical bonds are formed, which results in the creation of new substances with new chemical and physical properties.
That is excellent. And I assume that you'll have your notes with you because you carry around your chemistry notes always.
It'll be word for word at dinner.
I know it. I know it. Well, just repeating it once, I'm sure it's tattooed in your memory forever and ever and ever.
That's
All right, Matt, something you learned today you didn't know before today.
Probably like the difference between heat and like catalysts.
Very good. Very good. Very good. Let's see, who have we not heard from today? Bliss, something you learned today?
Like a catalyst is like it's a speed up reaction by lowering like the energy.
Sounds good. The activation energy specifically. Very good. Very good. We'll get one more. Kyle, what did you learn about chemical reactions or equations you didn't know before today?
You have to balance the equation after.
Which is what we will learn tomorrow. So I pray we'll be back together tomorrow in person and you'll get back your fantastically done exams and we will continue. No assigned homework tonight. Enjoy the rest of your day. Stay nice and warm.
Thank you. Have a good day.
Take care, guys. See you tomorrow. Bye-bye.
Have a nice day.
You too, sir.